Welcome everyone. Thank you very much for coming. So it's the first pre-seminar for this year. So first, thank you to Rob that came on his vacation just to take film of this seminar. We're going to have quite interesting year with quite interesting seminar, but the best way to start, of course, is with Martin. So Martin was very kind to have the first seminar for the year. I assume that all of you know Martin, but Alistair will give some words about Martin and his contribution to the center, and then we will hear his presentation. So Alistair.
Thanks very much, Ziv. Well, look, it's a pleasure for me to introduce Martin. Martin, of course, has been at the very heart and centre of photovoltaics for many, many decades, as everybody in this room is no doubt aware. So I won't take up too much time. It's good to see everybody here. I think next time, Martin, when we get you to speak, we'll have to get a bigger auditorium. But I'm really looking forward to hearing what Martin's got to say, and so I'll, without further ado, hand over to Martin. Thanks, Martin.
Thank you, Alistair. Thank you also, Ziv and Rob in particular, for coming in today. The last couple of years, we've seen quite dramatic reductions in the cost and prices of photovoltaic modules and systems, much more quickly than anyone could have anticipated. So what I'd like to talk about today is, the prospects for building on that better than expected performance to give photovoltaics a more pivotal role in addressing one of the major issues we're facing, how to control global CO2 emissions. So that's the topic of my talk today. Just as a preliminary, this is just some of the data showing the reduction in photovoltaic costs. This is module cost per watt, but they have literally reduced 15 times in 10 years. This is the average selling price as documented by multiple market research companies. So gone down from $4 US a watt till this month, the average is going to be 22 cents a watt. So quite really dramatic reductions. And that's been reflected in the system costs. Shown here are bids for power purchase agreements in different countries in the world. These are the lowest bids received for different technologies. And the red line just shows the trajectory of photovoltaics, slowly knocking off one after, or quickly knocking off one after the other of the incumbent technologies emerging as one of the cheapest options. So I've shown there also bids for some of the other options, and photovoltaics has come in lower than all, with the exception of wind, which has shown some lower prices since I prepared that graph. So we have seen bids as low as $17.86 US a megawatt hour for photovoltaics. That's the ultimate low, but obviously there's still scope for further improvement. The technology is still really quite in its infancy, and we expect the costs to go down. So how low can they go? At least to $10 a megawatt hour. That's 1 cent per kilowatt hour. So reaching new levels of low, I guess, for any energy technology, at least in present day dollars. There's been 3 or 4 actually milestones. This is just a graph from the carbon tracker project, but they I guess the vertical axis is volume and the other is timeline, but they identified 3, and I've added another one, milestones that photovoltaics has passed over recent years. The first was a few years back, I'm guessing 2014, when the cost of photovoltaics became competitive with the retail price of electricity, say for residential systems and that kind of thing. And the next was when the cost became comparable with a new coal-fired power plant. And as we saw in the previous slide, that was in 2016 when you started undercutting it. And the next milestone, so that was the cost of building a coal plant and operating it. The next milestone was the marginal cost of coal generation. And that previous slide showed that that was in 2017 that occurred, at least in the sunniest parts of the world. And the next big milestone is when the cost of firm electricity from solar, so solar available on demand, becomes competitive with that from traditional sources. And there is evidence that that's already occurred in some parts of the world, namely in Australia. This is just a couple of recent articles from Renewable economy, but Snowy Hydro, who operates the Snowy Mountains hydroelectricity scheme, has a combination of Australia's largest pumped hydro capacity in the Tumut 3 dam, shown there. So 600 megawatts, 15 gigawatts hour of storage. And also recently contracted for 888 megawatts of photovoltaics. I think there was a Chinese connection somewhere in that bid. But the types of prices that, well, the types of responses they got to that call for power purchase agreement suggests that the prices they were receiving for both wind and solar were in the Australian $40 to $50 per megawatt hour, which is getting quite competitive with some of the international costs that we saw earlier. So Snowy now maintain that they can offer firm solar and wind at prices below that of the base load prices that are prevailing in the Australian market. So $70 Australian a megawatt hour is what their estimate is of firm solar and wind capacity. So good news. The other good news was that the solar market appears that it has grown last year. So there's initially fears that a cutback in some of the Chinese programs would result in a drop in photovoltaic demand for the first time for decades this year. But some of the more recent reports are suggesting that the decrease in demand in China was more than compensated by increased demand in other parts of the world. And so Bloomberg, who published this just last week, suggests the market grew about 10% in 2018 and forecast somewhere between 10 and 25, 30% gain during the next year. Also shown there is wind, which is also expected to grow quite substantially in 2019. So for photovoltaics, that over this period shown here, 2010 to 18, corresponds to 25% compounded growth per year. So if you do the maths, if the industry can continue to grow at that rate over the next 10 years or so, you'll then be at a terawatt of photovoltaic installations every year, which is a very significant figure, as I'll try to demonstrate. Another, I guess, really good thing that happened during the year was that the UNSW PERC technology emerged as the technology now produced in most volume internationally. So this is just showing the capacity installed, but over 60 gigawatts of PERC manufacturing capacity installed, very quickly going from 25% of capacity in 2017 to an estimated 60% right now. So from now on, most solar cells that are produced will use the UNSW PERC technology. Another big plus for Australia was its market really grew quite dramatically. These are figures from Green Energy Markets, but showed the Australian market tripled in 2018. So, somewhere close to 4 gigawatts of demand. But largely, most of the increase coming from large grid-connected systems that are being installed frantically around the country. I guess the other good news is the market's expected to grow again next year. So a very rapid increase in the size of the Australian market, making us one of the big players internationally on the market. The bad news was global CO2 emissions increased. So this is latest figures for the CO2 emissions, but it looks like we're up to 37 gigatons of CO2 emitted internationally each year, with growth in most countries with the exception of Europe, that at least shown on this graph. This is a similar graph, but it was published in 2014, so didn't have all the data that the last one has, but it's very relevant to today's talk in that it is what got me thinking about just what impact photovoltaics could have. So the black line at the top shows, the emissions up to 2014, up to 35 gigatons. It has grown slightly as was expected here. So, maybe to the 37 that we actually saw in 2018. But, what's urgently required is a reduction in these. And this was one of these trajectories. Many have been published, including one recently by the IPCC. But this is a type of trajectory in CO2 emission reduction that's required to keep global temperature rise to below 2 degrees centigrade, with reasonable probability. But the importance of this graph, at least to me, was, showed that we've got a real problem in meeting that type of trajectory, in that what it did was extrapolate the emissions of the 4 biggest emitters. And you can see there's going to be a problem arising over the next decade when the combined emissions of those 4 emitters, despite their best efforts in curbing them, is going to use the whole budget for a 2-degree trajectory. So when I saw this in 2015, I was a little bit despondent in that, what chance have you got in this scenario? But if you look at what 1 terawatt of photovoltaics would look like, which, I estimate we'll reach that level on present trajectory somewhere between 2025 and 2028. This is what 1 terawatt of photovoltaics can do if it's displacing coal from electricity generation or oil from transport. This is the type of impact it'd have on CO2 emissions. So if you're installing, 1 terawatt a year, you're sort of on the right type of trajectory to come down that slope. So if other measures can keep the emissions through other processes, more or less constant, there's a possibility that terawatt levels of photovoltaics could reduce CO2 emissions globally on the type of trajectory that's required to meet some of these projections. So if we look at the sources of global CO2 emission, like electricity generation is the overall dominant one. And it's a little bit obscene in that it accounts for somewhere between 30 and 40% of total emissions, but the contribution to GDP is less than 3%. So it's really a disproportionate source of emissions compared to the economic value of the activities and all that kind of stuff. And fortunately, it's the obvious candidate for displacing by photovoltaics. Looking at applying photovoltaics to the conventional electricity network, a small amount tends to be good, particularly on days like today where we're expecting, strong demand in at least the southern states due to the high temperatures. So this shows Queensland about this time last year where a similar heat wave was passing through, and there was 3 days of record temperatures, so successive days bumped up the not record temperatures, but record demand for electricity. So successive days bumped up the previous record for peak demand. So this was the first, second and third. But the yellow bit shows the contribution of solar. Most of the solar, this stage is behind the meter so that it's not taken into account when the grid calculates its peak demand. But without the solar, you could see that the demand would have been very much higher. So a little bit of solar is really good, and that particularly in the summer months where it can cut down, on this peak demand, quite substantially in Queensland, as you can see. So the peak would have been, I think, this one here. So it's cut down the, the peak demand from here to here. So had quite a substantial impact. But at the time of this peak demand, the amount of solar available, roughly 1 gigawatt of solar, in Queensland was reducing the demand at the time where the actual peak occurred. So great. But when you get more solar, you run into additional problems in operating the grid in its traditional way. And this is from California, where the infamous duck curve, I think, first emerged. But, the blue line shows sort of the traditional type of demand that has to be met by the traditional generators. But as you add more and more solar, you create this dip here, which creates 2 problems. One is a decrease in demand for the traditional generators, as you can see here. But the other is, in this month at least, where the solar is dropping out before the evening peak, you increase the rate that the conventional generators have to take up the load. So both those things are bad. So special measures are needed to address it. You'll note here there's a suppressed zero, so this is we're dealing with small bits of electricity at the top of the supply, total supply. There's the duck if you can't see it. Although I see this as the duck body rather than this being its arched back. But we don't have to look to California to see even more severe problems. Like Australia, I believe, is going to be a pioneer in the adoption of solar, despite the best wishes of our present politicians. But you know, it's just going to happen just because of the economic incentives for installing solar. But this is South Australia and their projected demand. So not only do you get this duck with the very bent back, but the total demand actually drops below zero. So that's reaching a completely new domain, and we're going to do it well before California gets anything like that. So Australia is going to have to address a lot of these issues, I think, much sooner than other parts of the world, but I see that as an opportunity rather than a threat. It's a chance for new industries and companies to establish approaches for dealing with these issues ahead of other parts of the world, and therefore establishing a first mover sort of position, you know, within the world market. So, you know, one problem is, you know, it's very difficult to deal with this, you know, excess electricity available. You just throw the whole grid out of balance. So you're probably going to have to curtail it. And a lot of studies I've seen, you know, including those by Bloomberg, just count on all this electricity being dumped with zero value assigned to it, but still the strong uptake in solar of wind is the best economic scenario, even with when you're dumping that that extra electricity. But obviously, if you could do something with that excess, which we're going to get quite quickly, so you know, probably by the mid-2020s in South Australia, we're going to reach this situation. So we need to find something to do with that excess electricity, which is one of the things I want to talk about. The other issue is grid stability. So back in the 17th century, Christian Huygens noted that if had two clocks close to each other, they pendulum clocks, they gradually worked into synchronization with each other. And that's a general feature of, you know, weakly or at least coupled oscillators. They don't have to be weakly. Strongly, you'd probably bring it out more quickly. But if you have two oscillators of a similar frequency, if they're near to each other, they'll come into sync with each other at some type of intermediate frequency, I would imagine. But that's a principle on which the power grid operates. So they've got different generators operating, you know, different inherent frequencies, I guess, but the interconnection between them in the grid networks brings them automatically into perfect sync. The problem arises if some type of disturbance, like one of the generators dropping out or a power line going down, drives them out of sync. And then that's a disastrous system for the grid, because you get very large power flows in, you know, at least localized areas, and you can do damage and you know, severe damage and so on. So the grid has to disconnect and reconfigure itself. So within South Australia, we're already getting substantial curtailment of wind. So this was data for Q3 of last year, which is the most recent I could find. But about 10% of the generation of wind was curtailed, not because of the other problem, the generating more than the grid could handle, but just to leave enough synchronous generators online to provide, you know, the assessed level of stability that would be required if there was a disturbance and things went amok. They would quickly rectify themselves. So again, you know, there's electricity being dumped right now. If we can find something useful to do with it, it's essentially got zero value. If we can find something to do with it, you know, so much the better. You know, so what South Australia is doing is a couple of things. You know, one, they're pushing for an interconnector to New South Wales to strengthen the connection there, so connecting them to the strong grid in the southern states, and therefore, you know, mitigating this synchronous issue, synchronization issue, but also providing a market for all this excess wind generation. So, you know, double benefit. And the other thing you can do is you can add what are called synchronous condensers to the grid network. So this is what they're also planning to do, is stick some of them in critical parts of the grid. What these are really are, you know, a pretty traditional generator, but just not connected to any load. So it's just there, sort of spinning around, just providing that inertia that the grid needs. Interestingly, in other parts of the world, these synchronous condensers have actually been made using old generators that there was no more need for. So there may be a role for some of our coal-fired power stations in providing the synchronous generation if we're successful in displacing coal from electricity generation. Okay, you know, what can we do about the duck curve? So I've already mentioned a couple of things that South Australia is doing, but you know, just looking at it generally, and one of them is storage. And you know, the traditional electricity grid has had the need for storage, as I'll explain a bit more fully. But the way that has traditionally been addressed is using pumped hydro storage. So this is a scheme in Germany, but you know, when you've got excess electricity, you just pump water up to this reservoir up here, and then when you need it, you just let it flow down. So the round trip efficiency is about 70%, so you lose something in the process. When you look at where all this is installed, it turns out most of it is installed in Japan, although quickly being overtaken by China. You might ask, you know, why has Japan got a special interest in pumped hydro? If we look at the Japanese electricity network, I'll probably just look at the top curve there, the dark red one. It just shows the day of peak demand in 2002, I think. But if this is just monthly, so the peak is occurring here, that's midsummer. And then if we look at the time of the day when that demand occurred, it's occurring, you know, sometime in the afternoon, around 3 p.m. or something. So, you know, summer peaking grid in Japan. This little dip here, incidentally, is the workers going off for lunch. So creating problems for the grid in terms of the ramp rate required for the grid generators. Japan was keen to, pre-Fukushima, Japan was keen to increase the share of generation from nuclear because that provided a mechanism for energy independence for Japan that otherwise wasn't available. A lot of these, these pumped hydro storage systems were essentially installed to provide, if you like, storage for their nuclear power plant. You don't often hear about storage being required for nuclear power plant, but this was the case in Japan. So the graph over here shows a daily cycle. In Japan, the nuclear plants can only operate two ways, either flat out or completely off, because, you know, taking the nuclear plant through the transient state through moderating the power output puts extra stress on the components and so on, and their plants weren't rated for that stress. So in order to allow the nucleus to run continuously, you know, you couldn't afford to turn them off and on each day. Well, it wouldn't be technically feasible, I don't believe. But this pumped hydro was provided to provide a nighttime load for the nuclear. So you can sort of see the load profile here. I've sort of redrawn their drawing a bit with this dotted line. At nighttime, the pumped hydro contributes to the total demand, providing a minimum demand for the nuclear reactors to provide. Otherwise, they could get caught in a situation where the nuclear plants were generating more than the power system was able to accommodate, which would create problems for the grid, as I mentioned before. And then during the daytime, during the period of peak demand, you can see the hydro being discharged, very neatly being able to accommodate the lunch hour. As you can see there, they just turn these pumped hydro plants off during that period. This is data I compiled just from, you know, when all the different plants in Japan were commissioned, but the black line shows the pumped hydro plant to the right axis, and the green line shows the nuclear plant. So very close correlation in installation dates. And in fact, for every 2 gigawatts of nuclear that have been installed in Japan, there's been 1 gigawatt of pumped hydro. So quite substantial storage requirements for nuclear, which I've never heard any proponent of nuclear ever mention. After Fukushima, Japan revitalized its photovoltaic program, and both Japan and the US have now surpassed Germany as the country with the second largest capacity. They're battling it out for that position with over 50 gigawatts of photovoltaics in both countries. But Fukushima, Kyushu down here is the tropics of Japan, and it gets the best sunshine. This just shows, you know, a graph I noted from May of 2016, where interesting to see the pumped hydro is being reused as sort of in a reverse mode. So during the daytime, when the solar all kicking in, you're generating more power than the system really needs. But what it's doing is pumping the water back uphill during the daytime rather than it flowing downhill. And then at night time, to fill in some of the void left by most of the nuclear plants still being offline, you're discharging that and using it to provide some of the nighttime load. So just an interesting reversal. Australia doesn't have nearly as much pumped hydro as Japan, but we do have some. So they're listed down here in this region here, but Tumot 3 I mentioned before is the largest. But there's moves afoot being stimulated by ARENA to try and increase that pump storage capacity. So the pump storage has additional advantage of it provides some of this inertia in the system, whether it's pumping or generating. So it's a, you know, when you're using it to store electricity, you're still providing some of that needed inertia. So there's a number of schemes being investigated around the country, you know, with ARENA trying to build up the capacity quickly, as indicated in this little graph up here. But two I want to talk about are the Snowy Mountains, which you may have heard of, pumped hydro, and then the work at ANU on off-river pumped hydro. So this is Snowy 2 that you've probably heard about, but it's a grand plan for greatly increasing the amount of pumped hydro capacity in Australia, actually to a massive 350 gigawatts. 2 gigawatts rating for the plant in terms of the power output. A study by ANU, headed by Andrew Blakers, who gave a talk here last year on it actually, but he estimated to go 100% renewables in Australia, you'd need something like 20 megawatts of storage, 20 gigawatts, sorry, of storage capacity, so you know roughly 10 times larger than this, and about 500 gigawatt hours of storage if you had sufficient geographic interconnection of your generators. So this is doing very well in terms of the amount of storage you need. It's about 1 day storage of all the electricity generated in the Australian network. But this capacity is a little bit lighter than what Andrew would have liked. But this is a scheme, you know, basically I had to flip this slide around to get it to align with the actual geography, but this is the upper reservoir is this dam up here that's already existing, and then the lower reservoir is this dam, which also incidentally is the lower reservoir for the Tumot 3 scheme, which is, you know, up in this corner of the slide here somewhere. But yeah, just drilling through the mountains to connect the two reservoirs with a hydro station in between, or either a pump or a generator. So you know, so that scheme looks good. The main uncertainty is just the cost of doing all that drilling due to the, you know, needs more geology, more studies of the geology to get a firm idea of what the costs are. But a big risk because of the, you know, the high capacity and cost of the total system. So the ANU group, headed by Andrew, has been looking at another alternative off-river pumped hydro. So this is an example of one of those schemes that was installed in '79 in Presenzano in Italy. So they've just built a reservoir down here, a big swimming pool, and then another reservoir up here in the mountains. So this one's connected through, you probably can't see it, but there's connected through to this point, and here's the pipes that go down to the hydro generator here. So the head is about 500 meters, so that determines how much storage you can provide. So it's rated at 1 gigawatt and 5 gigawatt hours. So that's the example of, you know, how such a system can be built and work. But Andrew has been looking at using satellite imagery to look at possible sites around Australia, and he's found 22,000 of them that look interesting. So there's no shortage of sites. So what you're looking for is a high head, so the distance between the upper and lower reservoir. He hasn't worried about the lower reservoirs here, but the upper reservoir, you know, the uniformity of the terrain determines how easy it's going to be to build a large area of reservoir and that kind of thing. So that really sounds a little bit interesting, by you know, just picking the very best sites in terms of your energy storage capacity for the outlay you have to make in pumps and piping and drilling, all that kind of stuff. So this is just summarising what they found, but this is a Snowy scheme here, which is 350 gigawatt hours, but one particular site that he found in New South Wales had very similar capacity. You know, this was the largest site they found in their study, by building these artificial reservoirs rather than relying on dams already existing. And then in the other states there was also acceptable sites. So, pumped hydro storage looks like a really good option. Not only does it provide the storage, but also provides this inertia within the grid that you might need as you take up more and more renewable capacity. So Andrew also showed the Hornsdale battery, which is built as the world's biggest battery. Well, I think in fact it was and still may be the world's biggest battery. But you can see that the storage capacity is quite puny, only 0.13 of a gigawatt hour. But the battery is also providing some very useful services. So this is a photo of it, the big battery, world's biggest battery at the time of installation, possibly still, 100 megawatts and 129 megawatt hour storage. It's being used in two ways, and one is sort of arbitrage. So this is shown up here. The red line shows the, price of electricity within the South Australian market. So the idea is to, this is what it's paid for electricity within the South Australian market. So the idea is to use electricity when it's at a low price to charge up the battery, which is shown this purple region here, the price is low, and then during peak periods of, where prices are high, discharge the battery and so on. So buy low, sell high. So that's been working quite well, except, what the battery storage will do is help push up, if it was bigger, would push up the prices here and reduce them here. So, in its own success is its own demise, I guess. As you put more and more of this storage onto the grid, you're going to decrease the opportunities for arbitrage, as shown here. So that's one of the problems facing storage, which is probably a disincentive to investment. It might look good now, but by putting in your storage along with everyone else that wants to put it in, you're going to decrease it. The other thing that the battery is providing, and most of its capacity is reserved for this, is frequency control ancillary services, which is just providing excess capacity to keep the grid at its 50 hertz, very close to its 50 hertz. This was traditionally provided by gas generators, so you can see the costs of doing that. This is just a weekly summary of costs associated with providing these ancillary services. Suppliers bid into the market as for electricity supply itself. But the cost was really quite high, but as soon as the battery came online, the pricing became much cheaper. So, the battery providing a very much cheaper option than the traditional way of doing it for various reasons that I won't have time to go into. But saving, I guess consumers in South Australia, millions of dollars already in the first year of operation. So, providing, the batteries can also provide synthetic inertia to the grid network, so it can reduce the demand for inertia within the grid network to keep synchronization, to allow rapid resynchronization, I guess. So lithium-ion batteries are following a similar trajectory to photovoltaics. They're falling about 20% a year, as shown here, so batteries are going to become more and more feasible. I'll just mention another option because it's very strongly connected to UNSW and even to the photovoltaic group, but that's the redox flow battery. And it's a different concept from the lithium-ion battery, but the idea is you just have two solutions where the ions in that solution can assume two different charge states. And you get these solutions to interact through a membrane here. So you can charge the solution by changing the charge states in one direction, one goes up and the other goes down, and then discharge it by reversing that. So that's the basic idea. So the membrane doesn't let the ions in solution through, so it keeps them separated, but it lets the electrons through, so it allows that change in charge state. The first redox battery work here at the university was actually within the PV group. So one of my students, Robert Brand, actually built one in 1982 with some help from NASA, who had been investigating this concept. Oh, there's the battery built, but we were interested in iron and chromium as the electrolytes because both of them were very cheap. So that was the idea for a remote homestead. You could have a very big tank full of cheap electrolytes and store electricity for a week without adding much to your costs compared to storing it for a day. So that was the basic idea. But then Professor Maria Skylas-Kazakus became aware of what we were doing, and she said, well, you should be using vanadium because it has multiple charge states that allows you to use it for both sides. And then you don't have to worry about one of the big problems, which was preventing the ions crossing this membrane and getting the solutions mixed. So that was the birth of the vanadium battery, and this was the first paper on it, which I was fortunate enough to be a co-author. But the vanadium batteries is the other strong candidate. It's regarded as the second favourite, I guess, for these types of storage applications. It's quite a heavy battery, so it's not good for transport. But particularly in China and the US, there's many companies that are developing systems like this. So these shipping containers hold the membrane and that part of the circuitry and the pumps you need to pump the solutions around, and then you have storage tanks you'll see underneath there. But there's a group in Dalian in northeastern China that's trying to knock the Telsa battery off its perch if it hasn't already been knocked off, but they're aiming for a 200 megawatt, 800 megawatt hour battery using this vanadium concept to be housed in this building here, which apparently has been built or is being built. So these are the shipping containers with the membranes, and then these are the storage tanks that provide for the storage capacity. So that's, I mentioned as an aside, but that's another battery technology that may be useful in the grid network. It's the second leading candidate, I guess. Okay, just talking about other ways of handling this. I'll have to speed up here because I'm getting near the end of my time. But load switching is another opportunity, and that's already being used within the grid network, as we'll show here. But this is just some data that I found from this consultancy here. This is the day of New South Wales peak in the summer of 2003, just showing the division between residential, commercial and industrial loads. And this is winter. The interesting thing is, if you look at the residential load, it's biggest at night time, and well, why would that be? Got the lights switched off and TV's no longer on. But if you look at how that residential load is made up, now this is data from that study, of a 4.5 hour peak demand for that winter day, 2.5 gigawatts is being used up in providing off-peak hot water heating. So it's a massive load upon the electrical network, but occurs in night time. So in a way, it's sort of load shifting to adapt to the particular characteristics of coal generators. You want to leave them on, you don't want to turn them off at night. So the nighttime load's been filled in by this load shifting. So the purple line shows the demand for hot water, on demand, and then the off-peak, moves all this into the nighttime area to even out the load. There's a lot of other loads that are not critical that you could do something similar with. So, refrigeration is one, space heat, pool pumps. So shifting these loads, not to the nighttime, but to the middle of the day, would mitigate some of those issues that are arising with the uptake of renewables. New daytime loads is another one. If you put more loads in the daytime, if you can remove them from the nighttime, even better. But that's a way of filling in this void here. Again, there's a precedent in terms of nighttime loads. So this is a map of the Earth from space, and you notice this very bright region here. That's actually Belgium, where I spent some time in the 70s. Belgium had just completed its highway system, but it also completed installation of its first tranche of nuclear reactors. So this is the highway system way out of the cities, but one thing's instantly noticeable when you're driving on it, there's lights everywhere. There's every 50 meters, there's one of these lights blazing away. So I asked when I was there, why that was, and they said, oh, we needed a load for our nuclear plants at night. So I haven't been able to confirm that. I haven't found any authority that quotes that, but that was told me then, and it seems like quite sensible. It's just a massive load for their nuclear plants that makes Belgium visible from space. These, incidentally, are now being replaced by LED lighting, so things are taking a sensible turn. But what we need to do is something similar, but create new loads in the daytime, possibly loads that are more useful. So one of these obviously is electrical vehicle charging. This is from Norway, who are moving over to electric vehicles quite rapidly. So that's one. It's a very good application that increases demand during the daytime. Another one, desalination, might be another one. I'm just sort of tossing out a few ideas, but I think this is a really important area. If we're going to have all this free electricity in the daytime as solar uptake increases, if we can find something sensible to do with it, it creates opportunities for new industries and so on. So some of the particular characteristics is you don't want that application to need electricity around the clock. So intermittent electricity supply, small duty cycles, that kind of thing is ideal. So, you know, electric vehicle charging is one of those. Desalination mightn't be too critical when you do it, so that sort of fits into that category. So both New South Wales and South Australia have one that's only operated 10% of the time to keep it ticking over. So that, you know, that might be an ideal load for dumping some of the excess power initially. But the other thing that might be more useful is to generate fuels during that period. So, you know, a lot of interest in generating hydrogen fuels, but the cost of the electrolysis equipment and the electricity needed, and then the low round cycle efficiency has been the disadvantages. But then again, if you're just going to throw the electricity away, that may change the economics of hydrogen generation quite substantially. And rather than developing electrolyzers that have to work 24/7, develop one that has to work a few hours a day. What impact might that have on the design and the costs and so on? The opportunities there, I think. And the other one that might be very useful is CO2 removal. So this is a scheme that's operating, I forget where in the world, I think up in Alaska, where the idea is to capture CO2 from the atmosphere and then convert it to a mineral where it can be safely contained. I'll just finish up quickly. And the other big one is import-export. You know, if you could globally interconnect all the electricity generators around the world, you wouldn't have to worry about, you know, being night time or the wind not blowing here, because it'd be daytime somewhere or the wind would be blowing somewhere else. So you just pipe the electricity around to where it was needed. So one advantage from solar generation, of course, is you've got, you know, solar generated around the clock. This just shows what a couple of hours difference in location can make, different hours in terms of time zone. You know, this is New South Wales versus Western Australia, so a couple of hours time zone difference. Already you can see that, you know, New South Wales generation might be useful for WA peaks, and WA generation might be useful for New South Wales evening peaks. The Australian grid is not connected to WA, but there's very good reasons for connecting the grid due to, if we go to more renewables, because of the different distributions of sunlight and wind. So sunlight is mainly concentrated in the north, as you might expect, but the wind is concentrated largely in the south. So some good regions up in North Queensland. So providing more grid interconnection between the, you know, different generation centres is one way of decreasing the amount of storage required in the network. And this was a very big feature of the study by Andrew Baker's team, using strong interconnection to, you know, say, couple generation of wind in northern Queensland here, which is completely independent of that in the southern states, to, you know, to the grid. So you've always got wind somewhere. Okay, better move on again. Europe already has large grid connection, and they have a similar situation, plenty of wind in the north, plenty of solar in the south. And there's also a seasonal variation that helps. This is just Germany's supply of electricity last year, but the green is wind, so plenty of wind in, this is winter months there, less wind in summer, little solar in winter, compounded by snow on the modules and things, and then plenty of solar in summer. So the seasonal complementarity is also another thing you can take advantage, particularly with those extended interconnections. So how far can electricity be sent? This little graph here just shows the costs versus the distance. So, you know, AC is the normal way of sending it, but becoming more common for long distance transmission is DC transmission. And, you know, one of the advantages is the cost of distributing it, the cost of these towers and things that you need to distribute it. So that the towers are thinner, they require less space, less right away, if you like, so make it cheaper from that point of view. And also the conductors, because they're DC, with AC you get a skin effect, so you can't use the whole conductor effectively. So the conductors are cheaper because you can use them all. So the longer you go, the cheaper the DC becomes in relative terms. Its disadvantage is you have to convert the AC to high voltage DC at the start, which is like a like, I guess, and at the end you have to convert it back the other way, which is like an inverter, converting the DC back to AC. So you've got electronics, you know, in quite sophisticated, cutting edge electronics involved in those conversions. So how far can electricity be sent? This is DC, high voltage DC transmission lines around the world. So South America has a few that are 2,000 to 3,000 kilometres in length. The little blue dots are just like zero length connections where you connect one AC grid to another one through this DC connection, and then you can isolate them from some of the types of issues that I mentioned before. But the biggest one now has just been finished the end of last year, but it's in China. It's can transmit 12 gigawatts, so a fair fraction of Australia's total electricity demand, over a distance of 3,300 kilometres at a voltage of 1.1 megavolts, so very high voltage system. That's the limit of what you're able to do, mainly constrained by the electronics, I guess, at the moment. This guy here, Liu Zhenhua, was former head of state power in China. That's the largest power company in the world, but he was keen on connecting China over to Europe, which is on the edge of technical feasibility now. 5,800 kilometres, 5,600 kilometres. So you know, that would connect those widely separated regions with their different generation characteristics. A few political issues that I won't have time to go into, but that's the main disincentive. Okay, just to finish up, I'll just talk, the next biggest CO2 emission source is passenger cars, which account for 9% of emissions. So you know, going to electric vehicles is one way of addressing that, particularly if you're able to you know, don't just draw power from the grid, but if you're able to have dedicated supply of that power from renewable sources, you're sort of adding additionally to the uptake of renewables. So this is, I think it's a drawing rather than a photo, but a Tesla charging station, you know, that's on the drawing board at least. But you know, that's the type of thing that's needed to have maximum impact. So electric vehicles being taken up quickly. China, US, and Norway are the leaders. Somewhere over 1.2 million annual sales in 2017. Expected to grow quickly, as suggested here, over the coming decades. You know, freight is another one which has always been considered one difficult to address through renewable sources, but then Elon came out with his electric semi-trailer. So, you know, maybe an impact upon freight as well. There's been a group at Lappeenranta University of Technology in Finland, headed by Christian Breyer, who used to do a lot of the long-term analyses for the European Photovoltaic Industries Association, but he's moved to that universities now, and they've become specialists in analysing a lot of these issues involved with the rapid uptake of renewables and just what type of impact it might have. And I think their analyses have some credibility. But in terms of cumulative PV capacity, the yellow bits show their calculation of what the uptake could be. It's based on an economic analysis, assuming, you know, rates of decreases of costs and so on, associated with the different emerging technologies. But getting to about 22 terawatts of photovoltaics installed by 2050 for electricity generation. And I've seen a couple of other studies that have recently come up with a similar figure. So that's a figure that independent studies are sort of coming up with as something that may be likely. But then again, you know, through this transport application, he sees a very similar demand emerging a little bit later, but by 2050, you know, matching that from the electricity, purely electricity generation for normal electricity uses. If you can put the cells on the car, you've got even a more direct connection. I'll just mention that we're interested in that application here, so I'm trying to get a project going where we develop panels that look like solar paint. So you can you know, use the body panels as active solar generators. If you look at some of the other big emitters, you know, we've looked at the three biggest, but there's a lot of other ones to do with industrial processes and so on. And Christian Breyer's been working his way through them, just seeing, you know, what might be feasible on what type of time scale with these. And he came up with this summary last year. So by 2050, where the most optimistic alternative study comes up with about 20 terawatts of photovoltaic installed, he comes up with the 22 terawatts for electricity generation, another 19 for transport, and then he can see his preliminary study suggests there might be something like another 18 terawatts in chemical processes, 4 terawatts photovoltaic, 3 for CO2 removal, and then a few more he hasn't got around to looking to yet. But his conclusion is something like 80 terawatts of total may be feasible. So that's a very optimistic scenario, but his studies are backed by detailed analyses so that he can back up. If he was here, he'd be able to argue to the death to anyone that questioned his figures. But I really like his last comment. This is from one of his slides, the whole bit here. But please do not forget, no one has yet understood what $10 US a megawatt hour PV generation cost really means. So the full implications of those very low cost electricity generations that are now feasible, or feasible in the very short term, if not now, from photovoltaics, what the implications of that might mean. So that's an area I'm interested in exploring more fully in our work. I hope the talk has thrown a little bit of light on some of the issues involved. So thanks very much for your attention.
Thank you so much, Martin. Few questions. The best question will get who sounds like that from Jim Linda. Richard.
Give me a minute to reformulate my question. Thanks very much, Martin. Really, really interesting. I had a question in my head, but you really answered it when you got to the hot water and all that, because I think all this issue that we're trying to solve of what we do with excess electricity at some time of day was already, it's an old problem. The brown coal in Victoria used to do it, the nuclear in Japan used to do it. They deal with it with load shifting or storage or whatever. It's not new, it's an old issue. So it's not something we're creating. We have answers. I think we know how to do for a lot of these things, as you explained. Is there a problem though with low prices in the daytime, low price or negative price or something, with the value of electricity or the value of PV being much lower?
Okay, I'll just repeat the question as I understood it. So is there a problem with low prices due to the excess renewable supply? Yep.
The way you do that is you make the prices low. It's the way we always did. It makes off-peak in the middle of the day.
Yes.
And I'm sure this will come. It should come. But has anybody thought through the impacts of that from an economic point of view?
I guess my presupposition is that the prices are going to get very low in the middle of the day as more solar gets put in, because having to curtail demand and all that kind of thing. So it's going to be a low price regime. So that's going to, I guess, encourage investment in these kinds of other applications. So load shifting, there's already companies looking at banding together pool loads from multiple households and that kind of thing to try and provide a package that they can then market in terms of a variable load on and off. So I think I think the market forces will head in the right direction to do that. Although like today, the electricity prices aren't going to be low today, so it wouldn't be a good day to be storing electricity as off-peak hot water.
Do you think there will be enough natural resources like lithium for that demand that we're going to have for batteries and electric vehicles?
Yeah, that's a good question. The question was, is there going to be enough lithium and other resources for the things like batteries we're going to need? Yeah, I haven't looked closely at lithium, but I've looked at the corresponding case for materials for photovoltaics, so I'm quite conversant with that. But I guess with the pumped hydro, there doesn't seem to be any such issue because there's already 180 gigawatts installed worldwide and so on. I guess it'll just determine which technology wins through. And with the batteries for storage, there is the vanadium, and then you run into issues with the vanadium storage, so you might have to go back to the iron chromium, which is where we started with the redox battery. But it's a very important issue, as is you know, with so much renewables being installed, what do you do at end of life? And those type of issues are going to become increasingly important if photovoltaics is adopted at the terawatt level.
Other question? This side? Oliver.
So we are an engineering school here, and as Andrew Blake has also mentioned, and you referred to his talk, technologically we seem to have solved this problem. But something is holding us back, and it seems politically we don't have the same kind of progress that we've had technologically. Do you see any chance that the political forces come on board with this transition and that we can really kickstart this from that point of view or from that angle?
I'll just paraphrase the question for the benefit of the recording. You know, is there any chance that we'll get a more positive political will to support the adoption of renewables? Yeah, I think times are changing. You know, like who would have believed 5 years ago that photovoltaics would be talked about so much as a possible solution for large-scale electricity generation in Australia? Whereas I think anyone in a power company now believes, you know, that's going to be the case. We're going to have to find a way of using photovoltaics down the track because that's going to be by far the cheapest option available for generation. So I think times and opinions can change quite quickly, particularly when they're driven by economic factors, as they are now being driven by a lot of the photovoltaics uptake. So you know, I think it's economics that have driven the rapid uptake in Australia, you know, plus the RECs that are the credits that are available for installing quickly now. Yeah, I see a change, and then if we do get a recalcitrant type of government, I think people are getting sick of hot summers and things like that, so there's a chance there'll be a political pressure to for politicians with more moderate views that align more with the population at large to get into power.
When we talk about pump storage and off-river and things like that, obviously with solar, it's getting so cheap that developers, the money's pouring on board because there's money to be made, basically. And I'm just wondering if there's a figure there that says, well, as far as pumped hydro goes, at the moment, if the cost of the energy you can buy, i.e. PV, is vanishingly small, like you're talking about, what's the effective cost per megawatt hour of generation of pumped hydro if it's just buying some really cheap electricity and putting it when it needs it? And how does it compete with coal and other things? And why aren't developers just going, well, I can make money off building pumped hydro right now? Or is it not cheap enough for individual parties who want to make money to go off and just build pumped hydro at the moment?
Okay, that's a very good question. I'll just paraphrase it, but how do we finance these alternative storage schemes like pumped hydro? My paraphrase. Yeah, no, I think it's a very important question, and I think the difficulty in financing is, you know, one of the big disincentives to the whole thing. So, you know, the Australian government formally backing Snowy 2, I thought was really good, because then you know, you've got a chance of solving that problem, you know, even though it mightn't be done through the best mechanisms of market forces or whatever. At least it was going to get the thing built, because you know, as I mentioned, as you install more storage, you take away the economic factors that were responsible for generating the interest in the first place. So yeah, the uncertain financial returns is one issue. So traditionally with pumped hydro, it's been the losses that have determined the running costs. So you know, there's some maintenance costs and that kind of thing, but you have to buy electricity at one price and then you lose 30% of it or whatever. So 30% of that price is got to be the difference between what you buy and sell at. So there's been, you know, that's sort of put the price on it. But if you're getting your electricity for free, because otherwise it's going to just be curtailed, it removes that as an issue, I guess. If the electricity is free and you're losing 30% of it, you're not losing any money. So it just becomes the maintenance cost, I guess, then of storage schemes like the Tumult 3, which must be the way that Snowy Hydro is thinking. They're you know, going to get electricity very cheaply, particularly if that connector comes over from South Australia and they can get wind energy cheaply in the you know, when it's in excess in South Australia, that'll cut down the costs of something like pumped hydro, because you know that is the largest component of the cost. Is just the cost, a fraction of the cost of the electricity you have to buy that you have to waste, plus a small amount of maintenance and operation.
Neb.
Thanks again, Martin, for a great talk. Just a quick question: do you see any barriers for the PERC taking over the world as a technology? The
PERC solar, do I see any barriers to the PERC taking over the world? Well, I think it already has taken over the world, so if there are barriers, everyone's jumped over them. But yeah, so yeah, with any new technology, you run the risk of facing new issues, and in a technology that's so dependent on long-term durability as photovoltaics, you know, any change in technology carries a big risk associated with it. But I think, you know, largely due to the work of a lot of researchers here, we've now passed that hurdle with PERC, and people accept that it's going to work well in environment. It actually operates a couple of degrees cooler than the conventional technology because of the better back reflector, but I'm not sure if that's being factored into all the calculations and analyses yet. When I've told people that, some have seemed quite surprised, but that accounts for extra generation capability from the PERC, and you know, lower temperature probably means longer operational life as well.
You mentioned different regions around the world. My question is a bit naive, considering that many of the third world countries and so-called third world countries are positioned in the south. Are we seeing a remapping of economic and political factors, considering that solar energy could come mostly from those regions?
Yeah, so the question deals with the developing countries and the economic and political factors associated with them. Yeah, so like in our group here, I always saw ourselves in developing cell technology as a race against time. We had to get it cheap, quick enough that it could be taken up, you know, initially by China and India. As you could see, these countries were going to need more energy as they developed in the future. So I think we missed out on China, but we sort of caught India, I think, halfway along. So I've got a slide that I didn't have time to show, but over the last couple of years, India has cut back on it was following the Chinese example and installing coal generators as quickly as it could. But the last couple of years, it's cut back almost entirely on coal installations and is now installing photovoltaics at an accelerated rate. So we might have caught India about halfway through, but we still have, you know, a lot of Southeast Asia, South America and Africa to grow to their full economic prospects. So yeah, we may have caught those in time, in that photovoltaics is going to be cheaper than any other option for generating electricity, and it might encourage different types of networks and so on from what we've seen in the West. So, you know, more like mini grids and that kind of thing, rather than the large, you know, countrywide grids that have traditionally been installed. Yes.
Thanks for the inspirational talk, Mark. On that slide with source of global CO2 emissions, there is a bar which is almost big as a passenger car with 8% named Other. Do you know what that may correspond to?
That graph was that graph was from the International Renewable Energy Agency, but I did ask them that, and they did answer in part, but I couldn't find anywhere where there was a really complete breakdown given of those. You know, it was a nice graph in that it summarised things in a way that suited the talk that I wanted to give. But I couldn't get that information on the breakdown. But I imagine it's just a compilation of small things, all, you know, less than 1% or something.
Okay. There is the other seminar in the build environment, so we'll not compete with them. So let's thank Martin again for such a great talk.
Thank you.